Hello dear students, today we are going to discuss UG second year third semester paper mathematics, that is a real number system. On this, today we are going to discuss real sequences and convergence properties. After listening this class, the students are able to know how to define a limit of a sequence and a limit of a subsequence. Similarly, how to establish the relationship between convergent sequence and a bounded sequence, and we are able to know what is monotonic sequence, and we are able to prove every monotonic sequence is convergence if and only if it is bounded. Finally, the students are able to know the Cauchy's general principles of convergence for sequences. Now, we will go into the topics. Basic definitions. First, coming to the a sequence A is set of real numbers presented in an order starting with a first A, second A1, A2, like that. In that situation, we can say how we are going to define the sequence. After substituting n equal to 1 A1, n equal to 2 A2, n equal to 3 A3, like that, we can get in particular proper order A1, A2, A3. So, we are arranging that elements into in proper order, that is we can say a sequence. So, a function f which is mapping from natural number to real numbers. Yes, listen carefully, a function f which is mapping from natural number to real numbers, then we can say it is a real sequence. So, whatever the inputs we are going to take from natural number set. So, I am taking the whatever the questions or whatever the inputs, we are taking that inputs from natural number set, and the resultant vectors are coming into the real number system, then we can say this is real sequence. Similarly, we have another definition for sequence. If a function f which is mapping from n to c, that is inputs domain from natural numbers and result is in complex numbers, then we can say it is complex sequence. In our UG level, we are going to discuss real sequences only, that is function f which is mapping from natural number to real numbers only. On this, we have certain definitions. Now, coming to the first sequence definition. If xn is a sequence and if r1 less than r2 less than rn is strictly increasing natural numbers, then the sequence xn equal to xr1, xr2 up to dash is called subsequence of rn. So, if Sn is any sequence and xrn is a subsequence of xn. A sequence could be viewed as a composition of two functions. It may be several subsequences. For examples, let us suppose xn equal to n is a natural number, it is a sequence as Sn equal to or xn equal to n, and in this if I take 2n multiples, that is set of even numbers, or 3n multiples, set of 3 multiples, all these are comes under the subsequence of original sequence xn. So, here xn equal to 1, 2, 3, 4, 5 up to n infinity 2, and the subsequences of these sequence are x up to n, that is after multiplying 2, the numbers are 2, 4, 6, 8, that is set of all events. So, this x to n is a subsequence of original sequence xn. Similarly, let us take one more example, xn equal to minus 1 whole power n minus 1. If you put n equal to 1, we will get now n equal, after putting n equal to 1, we will get x1 is 1. If you put n equal to 2, x2 is minus 1, n equal to 3 plus 1, n equal to 4 minus 1. So, alternately we are getting minus 1 plus 1, minus 1 plus 1. Only these two numbers are repeating infinite number of times. So, in this is the sequence with finite range. So, totally we are having only two elements, minus 1 plus 1. So, this is the sequence with a finite range. Again, here we have two more definitions. After defining this sequence, what is range of sequence, and based on that range of sequence, again we have two more definitions, finite range, infinite range. First, coming to the range of sequence. Range of sequence means the number of distinct elements in the entire sequence is known as range of sequence. So, just see, after substituting n equal to 1, 2, 3 up to infinite, see how many different elements are there in that entire sequence. and count that if the number of different elements or the number of distinct elements are finite, then we can say it is a finite range. Or if the number of distinct elements are infinite, then we can say it is infinite range of sequence. For example, this is the best example for finite range sequence, that is xn equal to -1 whole power n minus 1 or -1 whole power n, you can take any one. If you put n equal to 1 plus 1, n equal to 2 minus 1, n equal to 3 plus 1, n equal to -1 plus 1, like that we will get the only two numbers are repeating infinite number of times. So, in this the range of sequence is only 2, that is 2 elements are repeating infinite number of times, that is one is +1, another one is -1. So, here the range of sequence is 2, that is 2 different elements. So, 2 is finite. So, it is known as finite range. If we take one more example, see here xn equal to the sequence -1 whole power n by n. If you put n equal to 1 minus 1 by 1, n equal to 2 plus 1 by 2, n equal to 3 minus 1 by 3, n equal to 4 plus 1 by 4, like that you will get infinite number of elements. One is -1, next +1 by 2, next -1 by 3, next +1 by 4, like that you can get the infinite number of elements. So, in this the number of distinct elements are infinite. So, it is an example of infinite range. So, it is an example of infinite range of sequence. And in these examples here, I want to find what is least upper bound and what is greatest lower bound. So, in this example, xn equal to -1 whole power by -1 whole power n by n. After substituting n equal to 1, we got x1 equal to -1. After putting n equal to 2, x2 equal to 1 by 2. So, these are the different elements, and among all these elements, the least upper bound is 1 by 2 and greatest lower bound is -1. That is, the supremum of this entire sequence is +1 by 2 and infimum of this entire sequence is -1. Next, coming to the limit and convergence. So, these are the two major definitions in convergence sequences, that is how to define the limit of sequence and how to define the convergence sequence. First, coming to the limit of a sequence. A real number L is said to be a limit of a sequence xn if every neighborhood of L contains all members of the sequence except for a finite number of terms. Equivalently, L belongs to R is, that is a limit of a sequence xn if for every epsilon greater than 0, however, a small value, that is xn belongs to L minus epsilon comma L plus epsilon for all values of n greater than or equal to n naught, then there exists n naught belongs to n. We write this as the limit n tends to infinite, xn converges to L, that is as limit n tends to infinity, xn equal to L. It means as n is reaching to infinity, the sequence xn is reaching to L value. If L is finite, then based on that L value, we have two more definitions. If limit as n tends to infinity, xn equal to L. So, in this case, we are saying L is a limit of a sequence xn, and based on this L value, we have two more definitions. One is convergence sequence, another one is divergence sequence. Suppose limit as n tends to infinity, xn equal to L. If L is a finite, then we can say the sequence xn is convergence sequence. So, what I am saying convergence sequence means limit as n tends to infinity, xn equal to L. If L is a finite, then we can say the sequence xn is convergence sequence. That is, it is converging to L as n tends to infinity, means n is reaching to infinity, the sequence value xn is reaching to a finite value L. So, in this case, we are saying it is a convergence sequence. The sequence xn is converging to L. Suppose L is infinite, that is as n tends to infinite, the sequence xn is tends to infinite, whether it may be plus infinity or minus infinity. In this case, we can say it is a divergence sequence. Okay, as limit n tends to infinity, xn is tends to plus or minus infinity, we can say it is a divergence sequence. Next, let us take some examples. See here the sequence xn equal to 1 by n for all n belongs to n. In this, I want to find the limit of a sequence. What is limit point in this sequence? So, if you put n equal to 1, 1 by 1, n equal to 1 by 2, like that up to after taking certain large values, that is as n tends to infinity, n equal to infinity, 1 by infinity. 1 by infinity means 0. So, 0 is the limit point of this sequence xn. But in this example 0 does not belongs to in this set. So, 0 is the limit point of the sequence xn where xn equal to 1 by n. Since each neighborhood of 0 contains infinitely many terms of the sequence 1 by n, but here 0 does not belongs to the set x, the sequence xn. Similarly, let us take one more example. Xn equal to minus 1 power n for all n belongs to n. In this also, if you put n equal to 1, 2, 3, 4 up to infinity, totally we will get only two different elements. One is plus 1, one is minus 1. So, these two elements only repeating infinite number of times. So, in this, what is the least element? What is the lower bound? Lower bound is the minus 1, upper bound is the plus 1. That is, in this sequence, it having least upper bound and greatest lower bound. That is, lower bound exists, upper bound exists. So, it is an example of bounded sequence. Okay. Next, coming to the Bolzano-Weierstrass theorem for sequences. This is one of the most important theorem in real number system. That is Bolzano-Weierstrass theorem for sequences. I will read what is the statement of this. Every bounded infinite sequence has a limit point. Yes, I will repeat once again. The statement of Bolzano-Weierstrass property or Bolzano-Weierstrass theorem for sequences. Every bounded infinite sequence has a limit point. Coming to the proof of this. Suppose let xn be the any sequence, be a bounded infinite sequence. Let Sn s equal to xn is such that n belongs to n, and the sequence xn being bounded, the set S is becomes bounded since xn is a infinite. So, S is a having the finite point. So, according to Bolzano-Weierstrass theorem, for bounded infinite sets, S must have a limit point L. This L being limit point of S, the neighborhood of L minus epsilon, L plus epsilon has infinite number of members of the set S. Next, come to the next theorem. Every convergence sequence is bounded, but not conversely. As this is also one of the important theorem. I will explain the proof of this also. See here, every convergence sequence is a bounded, but converse is need not be true. That is, every bounded sequence need not be a convergence sequence. For this here, I will give the one example. As here, previous example, this xn equal to minus 1 power n is the best example for this theorem. That is, every convergence sequence is bounded, but bounded sequence need not be a convergence. See here, in this example, xn equal to 1 by n, sorry, xn equal to minus 1 power n. In this, lower bound is minus 1, upper bound is plus 1. So, it is a bounded sequence, but it is not a convergence. Why? Because limit as n tends to even numbers, x tends to 2n, x tends to infinity of x of 2n, which is equal to plus 1, and a limit as x tends to infinity of 2n plus 1. So, if you split these sequence into even numbers, even sequence and odd number sequence, as even terms, as limit n tends to infinity, the sequence value will goes to minus plus 1. As odd terms, the sequence value as n tends to infinity, sequence value will tends to minus 1. Of course, both are finite, but both are not equal. That is, limit as n tends to infinity, x of 2n does not equal to limit as n tends to infinity, x of 2n plus 1. It means it is not a convergence. Both are tends to finite value, but they are not equal. Minus 1 does not equal to plus 1 means it is not a convergence, but bounded sequence. So, it is an example of bounded sequence, but not a convergence sequence. Okay, this is the one of the example for this theorem. Next, we have one more theorem. Suppose xn be the any sequence which is convergence to a point L. Suppose same that sequence xn is convergence to another point M. Let us suppose limit as n tends to infinity, xn tends to L. Similarly, limit as n tends to infinity, xn tends to M, another point M. In this case, the both values m and L and m are always equal. It means limit if the sequence xn is convergence to L and the sequence xn is convergence to M, then L equal to M. This is. Next, come to the some more properties based on limit of a sequence. Suppose an and bn are two sequences is such that limit as n tends to infinity an equal to L and limit n tends to infinity Bn equal to m. So, limit as an tends to an is converging to L as n tends to infinity and Bn is converging to m as n tends to infinity. Then come to the properties. First property, limit as n tends to infinity, an plus bn is always equal to L plus m. Second property, limit as n tends to infinity, an into bn equal to L into m. Similarly, if L not equal to 0, then limit as n tends to infinity, bn by an equal to m by L. Here L not equal to 0. Next, sandwich theorem. In this is a major theorem, that is sandwich theorem. Based on this, we have certain problems also. First, let me discuss what is sandwich theorem and how we are going to prove this result. See here, if an less than or equal to bn less than or equal to cn for n greater than or equal to k, if an and cn are converges to a limit L, then the middle sequence bn is also converges to same that point L. So, what is the meaning of this statement? If an less than or equal to bn less than or equal to cn. So, I am taking bn is a sequence in between an and cn, and here an is converging to L and cn also converging to L. Then according to sandwich theorem, bn is also converges to same that limit point L. Now, coming to the how to prove this result. For proving this result, let us take delta greater than 0, since an is convergence to L as n tends to infinity, which is given in the statement itself. Similarly, I am using that result. An is a convergence sequence and Cn is a convergence sequence. First, coming to the An converges to L as n tends to infinity, then there exists n1 is such that mod of An minus L less than delta for all n greater than or equal to n1. Similarly, we can use Cn convergence definition. Similarly, Cn is converges to L as n tends to infinity. Then there exists one more element n2 belongs to n is such that mod of Cn minus L less than delta for all n greater than or equal to n2. If you club from these two definitions of convergence sequences an as well as Cn, we can define let n equal to the maximum value of k comma n1 comma n2, then for all n1 n greater than or equal to n. It implies an minus L less than or equal to bn minus L less than or equal to Cn minus L. So, which is given the statement conditions here, an less than or equal to bn less than or equal to Cn. So, from that statement, I am subtracting L from three quantities, that is an minus L less than or equal to bn minus L less than or equal to Cn minus L. And similarly, if you take multiply with minus symbol, automatically less than will become greater than, that is an minus L greater than or equal to bn minus L greater than or equal to Cn minus L. That is step I am writing like this, that is L minus Cn less than or equal to 1 minus bn less than or equal to 1 minus n. From these two quantities, we can write modulus of bn minus L is equal to maximum of bn minus L comma L minus bn, which is less than or equal to maximum of Cn minus L comma L minus Cn, or again which is less than or equal to maximum of Cn minus L comma An minus L. Thus, implies modulus of bn minus L is always less than delta for all n greater than or equal to n. It means bn is satisfying the convergence condition, that is modulus of bn minus L less than delta. It means limit as n tends to infinity, bn is tends to L value, that is bn is converging to L. So, according to this sandwich theorem, if a and bn are convergence to L, then bn is also converges to L whenever an less than or equal to bn less than or equal to Cn for all n greater than or equal to k. Okay. This is sandwich result or sandwich theorem. Next, monotonic sequence. Coming to the next definition, monotonic sequence. First, coming to the what is the meaning of monotonic sequence. Before going to discuss this monotonic sequence, we have to learn about two more definitions, that is monotonic increasing sequence, monotonic decreasing sequence. First, coming to the what is the meaning of monotonic increasing sequence. Suppose xn is any sequence is said to be monotonically increasing sequence if xn plus 1 is always greater than or equal to xn for all n belongs to n. So, I will repeat once again, a sequence xn is said to be monotonically increasing sequence if xn plus 1 is greater than or equal to xn for all n belongs to n. Means as n is increasing, the sequence values also increases. Then we can say it is monotonically increasing sequence. Suppose coming to the next, monotonically decreasing sequence. So if xn is the any sequence and this sequence is said to be monotonically decreasing sequence if the condition is xn plus 1 less than or equal to xn for all n belongs to n. Means it means as n values are increasing, sequence values must be decreased. Then we can say it is monotonically decreasing sequence. By using these two definitions, again we can discuss the two more definitions: strictly monotonic increasing, strictly monotonic decreasing sequence. So the difference between monotonically increasing sequence and strictly monotonically increasing sequence is, if it is monotonically increasing sequence, simply we are writing xn is a sequence and xn is said to be monotonically increasing if the condition is xn plus 1 is greater than or equal to xn for all n belongs to n. If I say same this strictly monotonically increasing means we can remove that equality property. That is, xn is a sequence is said to be strictly monotonical increase if xn plus 1 is only greater than, I am not taking greater than or equal to, strictly it is greater than. So xn plus 1 greater than xn for all n belongs to n. Then we can say xn is a strictly monotonically increasing sequence. Next, coming to the strictly monotonically decreasing sequence. So a sequence xn is said to be strictly monotonically decreasing sequence if xn plus 1 is strictly less than to xn for all n belongs to n. Then we can say it is a strictly monotonically decreasing sequence. By using all these definitions, now coming to the monotonic sequence. Yes. Now come to the how to define this monotonic sequence. A sequence xn is said to be monotonic sequence if it is either monotonically increasing sequence or monotonically decreasing sequence. Then we can say it is a monotonic sequence. So it should be either monotonically increasing or monotonically decreasing. Then we can say the given sequence is monotonical sequence. Okay. Next, coming to the theorems. A monotonic sequence is convergent if and only if it is bounded, as this is an important result in monotonic sequences. A monotonic sequence is convergent if and only if it is bounded. Next, by using all this, we have two major theorems in this real number system and sequences, that is Cauchy principles or Cauchy sequences. The first one is Cauchy first theorem and second one is Cauchy's general principle. Let me discuss one by one. First, Cauchy's first theorem. According to this, it states that if an converges to L as n tends to infinity and Bn equal to a1 plus a2 plus divided up to an by n, then Bn is also converges to same L as n tends to infinity. It means if an is a convergent sequence and Bn is defined like this, Bn equal to a1 plus a2 plus divided up to an by n. If Bn is defined like this, then the sequence Bn is also convergent to same that L point as n tends to infinity. Now coming to the proof of this. Given that Bn equal to a1 plus a2 plus a3 plus up to dash an by n and I am subtracting L on both sides. So Bn minus L will become a1 minus L plus a2 minus L plus divided up to an minus L divided by n to show that Bn is converges to L as n tends to infinity. For proving this result, I am using without loss of generality. Yes, without loss of generality, we may assume that L equal to 0, then let epsilon greater than 0, the sequence an converges and hence it is bounded. Therefore, lambda greater than 0 is such that modulus of an must be less than lambda for all n. Since here an is a convergence sequence as n tends to infinity, then there exists a number capital M which is belongs to n is such that for all n greater than or equal to m, mod of an must be less than epsilon by 2. Let us assume k equal to 2 lambda m by epsilon, then for n greater than or equal to k, we can get Bn equal to, that is after applying the modulus on both sides for Bn, mod of Bn equal to. So what is the assumption of Bn? It is given in the statement itself, that is a1 plus a2 plus divided up to an by n. So, mod of bn will become mod of a1 plus a2 plus divided up to an by 2. If you apply inequality property, if you split the modulus property, equality will become less than or equal to. So, mod of a1 plus a2 plus divided up to an divided by n must be less than or equal to mod of a1 plus mod of a2 plus divided up to mod of an by n, again which is equal to less than m lambda by n plus n minus f. This I am writing sum of two quantities, that is mod of a1 plus mod of a2 plus divided up to mod of am by n plus next after m it is m plus 1 m plus 2 like that, mod of m plus 1 plus mod of m plus 2 up to mod of an divided by n. So, which is again less than or equal to, the first quantity will become m lambda by n and the second quantity will become n minus m epsilon by 2n, which is less than epsilon by 2 plus epsilon by 2, again which is equal to m, that is mod bn is equal to epsilon. It shows that mod of bn minus l less than epsilon, or simply limit as n tends to infinity, bn can be tends to 0, that is bn converges to 0 as n tends to infinity. It means bn is also convergence sequence. When an is a convergence to some point L, bn is also convergence to that L as n tends to infinity. This is Cauchy's first theorem. Next, coming to the Cauchy's general principle. Now, coming to the statement of this Cauchy's general principle, a real sequence is convergent if and only if it is Cauchy's sequence. What is Cauchy's sequence? As every Cauchy sequence means this first property, Cauchy's first principle is, if an is convergence to L as n tends to infinity and bn equal to sum of a1 plus a2 plus up to an by n, then bn convergence to L as n tends to infinity. With the help of this, Cauchy's general principle states that a real sequence is convergent if and only if it is a Cauchy's sequence. Now, coming to the proof of this. Suppose an converges to L as n tends to infinity and epsilon greater than 0, then there exists n such that mod of an minus L less than epsilon by 2 for all n greater than or equal to n. Hence, for all m and n greater than or equal to n, we have mod of a minus n. This is the definition of Cauchy's sequence, mod of a minus n less than or equal to, as you can adding and subtracting L value, mod of a n minus L plus mod of L minus n. So, actually before this we can write one more step, that is mod of a m minus a n is equal to mod of a m minus L plus L minus a n. Then afterwards you can split the modulus condition. So, after splitting the modulus, it will become modulus of a m minus L plus modulus of L minus a n, which is always less than, first one is also epsilon by 2, second one also epsilon by 2, because in the statement itself we given a n is a convergence sequence, that is modulus of a n minus L less than epsilon by 2. Similarly, modulus of a m minus L also less than epsilon by 2. If you substitute the two values here, epsilon by 2 plus epsilon by 2, it will become epsilon, that is mod of a m minus a n is equal to epsilon. It means every Cauchy sequence, actually we are taken a n is a Cauchy sequence. At the beginning we are taken a n is a convergence sequence, that is mod of a n minus L less than epsilon by 2. But afterwards, finally we are proved it is a Cauchy sequence. So, what is the definition of Cauchy sequence? Modulus of a m minus a n less than epsilon. So, every convergence sequence is always Cauchy sequence. Suppose a n is a real Cauchy sequence without loss of generality, let epsilon equal to 1, there exists a case such that modulus of a m minus a n less than 1 for all m comma n greater than or equal to k. In particularly, mod of a m minus a n less than 1 for all n greater than or equal to k, or a n minus 1 less than a n less than a k a n plus 1 for all n greater than or equal to k. Let lambda and mu be the least and the greatest numbers of the given set. So, the set of a1, a2 up to an up to a k plus 1, then lambda less than or equal to a less than or equal to mu for every n. Hence, a n is a bounded. This means that a n has a limit point, say L, and a n has a subsequence a or n such that a or n converges to L as n tends to infinity. So, it shows the real sequence of convergence is Cauchy sequence. If and only if it is a reverse case, that is conversely every Cauchy sequence, every convergence sequence is Cauchy sequence. That is first case. Second case we proved if it is Cauchy sequence, then automatically it is with the help of this result it will tends to convergence sequence. So these are the two different cases. First case I taken convergence sequence, n is a convergence sequence, then I proved it is Cauchy sequence. Second case I taken n is a Cauchy sequence, then finally I proved it is a convergence sequence. So a real sequence is convergence if and only if it is a Cauchy sequence. So if it is Cauchy sequence, it is convergence. If it is convergence, it is Cauchy. Next, coming to the one examples based on this. Let us suppose a n equal to 1 by root of n square plus 1 plus 1 by root of n square plus 2 divided up to root of n square plus n for all n greater than or equal to 1. Show that a n is convergence to 1 as n tends to infinity. With the help of this Cauchy's principle and Cauchy's general principle, I will going to explain one example. So a n equal to 1 by root of n square plus 1 plus 1 by root of n square plus 2 divided up to 1 by root of n square plus n for all n greater than or equal to 1. We have to show that a n is convergence to 1 as n tends to infinite. So since here 1 by n square plus 1 is greater than or equal to 1 by n square plus k is greater than or equal to 1 by root of n square plus n for 1 less than or equal to k less than or equal to n, and after simplifying all these, finally we can get 1 less than root of 1 plus 1 by n less than 1 plus 1 by 2n. Now root of 1 by 1 plus n is convergence sequence as n tends to infinite. Therefore by sandwich theorem, the middle term 1 by root of n square plus k is also tends to convergence, that is as n tends to n convergence to 1 as n tends to infinite. Okay. With this we stop our class. Okay. Thank you.